Okay, we are ready. So 10 o'clock. Yeah, if you haven't put your email in the chat box, go ahead and do that whenever you're ready. You can wait a little, doesn't matter as long as you do it. So we are gonna do lesson 2. So this is describing data part 1. So we obviously have next week we'll do a little bit more of it. A lot of our chapters are kind of split into 2 parts because there's a lot of information. So, usually we'll do like the basis of the stuff, and then the next week we'll kind of get more in depth about it. So, all right, variables. I've been talking about these for a while. I swear these are fun. So basically, variables, they vary. This is just a review. Stop me at any time if you have questions, or if I'm going too slow or fast, be like, stop that, like pick up the pace, girlfriend, like, yeah, or like slow it down, like, ooh, yeah. So just let me know. This is for you guys, like I said before. So I will do whatever you guys need. So all right, so let's talk about variables. So we have 2 different types, categorical and quantitative. So we'll start with categorical. These are going to be variables that are just different names. These have to do with just different flavors, colors, we went over this. And then you have nominal and ordinal. So nominal variables are going to be, they don't have an order to them. So like colors is an example. Unless you're talking about the rainbow, there's that Roy G. Biv thing, but that doesn't count. I'm just talking about other colors, so it's okay. Like periwinkle doesn't come before like maroon, so not really sure where I got those colors from. So yeah, that's an option for nominal variables. And ordinal, they have some sort of order to them. So we're talking about like elementary school, middle school, high school. They're still categorical, but they have some sort of hierarchy to them, so that would be an ordinal variable. And then quantitative variables have values attached to them. So and they're numerical, obviously. So these are going to be like 1 is always going to be smaller than 100 type thing. Yeah, a meaningful order. They always have a meaningful order. That's what I meant by 1 is always smaller than 100. Discrete are going to be, they can only take on a set number of values. I always think about like people, things you can't like split up. Lava lamps, I have one right here. That's why I looked at it. It's really cool. Check that out. Yeah, so that's why I used it as an example. I can't cut my lava lamp in half, so that's going to be discrete variables if I'm like, counting lava lamps. I mean, yeah, no, you can't. I was going to make sure, but yeah, so that's an option if you're counting them. Continuous are going to be more like measurements, so that's like things on like a number line. So I always think of weights, heights, anything like in centimeters, inches, stuff like that. There's going to be continuous variables because they can just take on any value. So I won't harp too much on that. I think you guys got that down. So here's some of the new stuff. So we have quantitative data displays, and the reason why I went over that is because you want to make sure you understand those in order to know when to use these different data displays. So you want to understand what quantitative is, so you know that these are quantitative data displays. They're displaying numerical data. So we have box plots, which I have the first picture on the right there. So this is really good for looking at like your 5-number summary we'll talk about, but your minimum and your maximum, it's a really good visual for that. Let me see if I can annotate. Such a weird word. Okay, so yeah, these are really good for, and then breaking it into quarters, because each part of this is, that's a quarter here, this is another quarter within here, another one, and then another one. So, you have 4 different, breaks it up into 4. This is the middle 50% that they're showing right here. So then obviously this is the 25%, the upper 25%, and down here is the lower 25%. This is good to use for percentiles if you're specifically talking about like we refer to them as like quartiles, because they're quarters. And the line in the middle is always your median, not your mean. So that's what that's going to be. So Okay, cool. So then side-by-side box plots, they're box plots, but the only difference is it's when we're comparing two groups or more. I mean, you can have a bunch of box plots chilling on there, but this is good at comparing things like, difference between, maximums, minimums, medians. So like it's very clear to see, in this case, like for women, this is age and gender down here. Wow, that's a good jump. Okay. So we can see the maximum for women is much higher than men. The median is higher for women. We could look at, the line there. So it's just a good way. It kind of looks like a dude. Look at him. He's so happy. Okay, so yeah, this is. I'm sorry. You gotta keep yourself happy when you're talking about statistics. Just gotta keep that smile going. So yeah, so that's what this is a good way to compare those two different things. So remember, these are quantitative data displays, and we use them. So we're going to use them when we have numerical data in that case. So okay, so a few more. We have histograms and dot plots. They're basically the same thing, minus the fact that histograms are used for larger data sets because you can represent a lot of data in one of those bars. When dot plots, each dot is a set of data, so you're not gonna have 100 dots in a row. I mean, you can, but you'd need a big old piece of paper, So histograms are better for those large sets of data. But yeah, the disadvantage of histograms are, unlike dot plots, for histograms, they are, you can't see individual observations, you just see the big range from, the minimum to the maximum type thing. So yeah, that's the difference between them. They're really good at looking at the shape of your data. That's like an easy way to look at it. So yeah, let's keep going. Okay, so z-scores. These are things everyone kind of gets tripped up on these every year. So z-scores, it's a way to standardize whatever data you have. So if you have data and it's in a normal curve and you have points on your data set, the z-score is basically taking those points but putting it on a new graph on the same distance from the center, but they're going to be standardized on a graph that has a mean of 0 and a standard deviation of 1 instead of your initial graph with your data and the mean and standard deviation that had. So yeah, this is always tricky for people to wrap their head around, which I totally understand. It's definitely a tough concept. So yeah, and like I said, it's the difference between the individual score and the mean. So your z-score is going to be, if we draw a normal curve here, and your z-score is always going to, like I said, it's going to be where you have a mean of 0, and then if I drew out here, your standard deviation would be 1. That's going to be, this is your normal curve that you're looking at, and your z-score is going to be whatever value, how far away it is from the mean. So let's say you have, over here it's 2.1. For example, that could be a z-score. It's saying that your score is 2.1 standard deviations above the mean. So that's what a z-score describes. So yeah, just understand what it is, as well as, and then down here, this is just how to calculate it. So you just want to use your original score, and then, or your original individual score, and then the mean of your distribution here, and then your standard deviation of the original distribution. So that's how you get your z-score. So basically these are coming mostly from your original distribution that you had there. And basically this over here is just algebraically switching this one around, so it's not really a new equation. You could find this using this equation too, but it's just algebraically switching it around. So, but it just makes it easier to see, that this is your original score, and then this is how you do it. So, okay. Like I said, stop me at any time if you're confused. The chat box is really weird in this. It's different than what I'm used to. So if I miss your question, yell at me or something. I have thick skin. I can be yelled at. Don't worry. Okay, shape. Go, yeah, I can do that. So let's go. Let me see on this one. Can I? Yeah, of course. Can I like add a? On my other on Blackboard, I could like add a random page. All right, I'll just do what I can on this one. Okay, so let's just do an example as if, let's say that I had a curve here that I got data from. That's a nice one. Oh yeah, that's really good. You could tell I draw normal curves on the daily. This is just, I'm in class and I'm just like, nope, just doodling some normal curves. So let's say that I got this, this is just an example. So I'm making up these numbers. We didn't get them from anywhere. But let's say I found a distribution and it had a mean of like 28. And I'll even write this over here. So we'll just say my mean is going to be 28. And then my standard deviation, and since this is a sample, that's why I'm using these, what do you call it? Symbols? Yeah, that's what I meant. Okay, yeah. So, and then standard deviation of, let's say, 6. Okay? So that means that one standard deviation above the mean, so right here, I'm going over 6 units, okay? And it stopped me if something doesn't make sense while I'm doing this. So I'm going over 6 units because standard deviation, remember, is the spread. So one standard deviation is going to be how much your standard deviation is over from the mean, however far away. So this is one standard deviation that I just drew here. So we would add 28 plus 6. So we're going to get 34, mental math. And so you get 34. So that's going to be your, that's going to be one standard deviation above the mean, okay? So then basically what a z-score does is it standardizes this. Oh no. That was just, how do I, oh, I can undo. Wait, do it. Oh, bless up. Okay, let me try this again. So, yep, that's much better. Okay, so now what I'm going to do, oh my gosh. So now what I'm going to do is I'm going to standardize, I'm going to make sure this is good. I'm going to standardize those original scores right there. So this one down here, actually I should make this a different color. So let's say, so down here, this is going to be our z-score curve. So remember, for z-score curves, we're always going to have a mean of 0 and a standard deviation of 1, okay? So in this case, here's our mean. It's aligned with the mean of 28 in the other one, so our mean is going to be 0 here. And then standard deviation is going to be 1. So if I were to go over 1 standard deviation, I would get 1. So if you were to be asked what is the z-score of 34, the answer would be 1. Because we standardized this 34, because this 34 is 1 standard deviation away from the mean. So if we standardize it 0 to 1, that means that if our mean is 0, 1 standard deviation away from the mean would be 1. So this is going to be our z-score. So in this case, you can even see if we were to actually do this, like let's say we did this equation, we would do z equals our 28. Where does it go? 34, yeah. 34 minus 28 divided by our standard deviation, which is 6. So then you're going to get 6 divided by 6, which is equal to 1. So you get the same thing if you do it with the equation, but this is just a visual of how that works. Does that make sense to everyone? Okay, cool. So sometimes it confuses people, but huh? What do you mean, huh? What part are you confused on? Oh, okay. Are you sure? Okay. Seriously, if you're confused, like, don't just say you're fine. Like, that's why I'm here to help. But, okay, so yeah, I hope the visual, I'm just showing you how you're just looking at the position of your original score as if the mean was 0 and the standard deviation was 1. If I were to go over 2 standard deviations, this would end up, so this is another 6. So I'm going to add 12, 28 plus 12. So my mean plus my standard plus 2 standard deviations, which is going to be 12. So that'll be 40. And then if I standardize that, that's going to be 2. 2 standard deviations away from the mean. So for our original score of 40, which is 2 standard deviations away, 1, 2, this is going to be 2, your z-score is going to be 2, because on a curve with a mean of 0 and a standard deviation of 1, it'll be 2 standard deviations away from the mean. Maybe, maybe not. Is anyone like completely lost? Like, let me know. I'm telling you, this chapter is like, sometimes it's a little confusing. Going once. Okay, like I said, stop me at any time. Oh my gosh, okay, got it, sweet. All right, we will continue on because I think we talked enough about z-scores. Hopefully there's not any more. See, that's what I'm talking about. Why does it keep all this on here? Like, why would I want this on the next slide? Like, this is just doesn't make sense to me. Okay, can I clear this? Okay, here we go. I'm sorry, bear with me. I'm still learning how to use Zoom. Okay, so shape. I'm in love with the shape of you. Okay, so shape is going to be, I know, Blackboard, see, I don't know. I don't know. I like Zoom for, you know, a lot of reasons. It's very user-friendly and it's more advanced and stuff. There's a lot more, like, features to it, but I was just so used to Blackboard that it was like, yeah, that's another thing. People would have a lot of problems getting into Blackboard and then they get kicked out and like, I don't know. So we're trying to get the best of both worlds, but this one's kind of easier, I think, because like you just click on my link and then you're boom in the room, you know, so it's just like boom in the room. But like, so I think like, I don't know, but we'll deal with what we got. I feel like as the semester goes on, I'll find cooler things to do. What is Spotlight? Whoa! This is cool. Shape. Wow. Okay, this is what I want always. Okay, this is cool. Okay, so shape. So remember, still talking about quantitative variables. That's why we reviewed that stuff at the beginning. So you got to remember what quantitative variables are. So we usually discuss them in terms of their shape. We're just talking about basically what they look like. Are they symmetrical, skewed, whatever. You can talk about how many peaks are in it. So peaks, wait, why? Can I draw? What is happening? Wait, I got this, don't worry. Okay, so like bimodal would be something like this. Or like, so this would be unimodal because there's only one. Here's 2. So symmetrical is just, it should be center. Same on both sides, a mirror image, so you guys probably get that. Okay. All right, so going more into shape, skewed distributions are going to be where one side is more spread out than the other. So this is something I know a lot of people sometimes can't get straight in their head about, like which one is skewed to the right, skewed to the left. Just remember, it's skewed to whatever side that the values are more spread out. So as you can see here, like for skewed to the right, on this left side, the values are really close together here. But then on the right side, they're much more spread out. You know, it goes from like here to here. So that's why this is going to be skewed to the right, because the values are much more spread out over here. We also call that positively skewed because this is our positive side of the graph. And then same with skewed to the left, this is going to be our negative. Also, you know, so this is negative skewed, or yeah, negative skewed to the left. And our values are more spread out down here on the left. There's a visual down here of quartiles. So remember, this is always going to be our median here in the middle line. And then, you know, we have our minimum and our maximum. And we'll go more into box plots. And then our quartiles are shown here. So, and remember, so our Q2 is always going to be our median, just as a review. So yeah, okay. Let us keep trucking. Here's a lot of stuff. Oh, I'm still annotating. Stop. Okay. Okay, central, nope, don't do that. Okay, central tendency. So this is basically how we look at our numbers in regard to one another. So you guys, I know most people have these like already. You guys remember these from other math classes. So our mean is our average. So you add up everything and you divide it by however many items you had. Median is your middle ground. So that's going to be resistant to values. So if you have 7 numbers, like let's say, click. Okay, let's say, you know, I have like 1, 2, 7, 10, 14. Our median is going to be 7, because that's the middle number, as long as that makes sense to everyone. And then, but it's resistant because if I changed 1 to negative 2,000, 7's still our median, because you like, if you did remember this thing, I did this in elementary school where you cross off each side, you know, it's position. You know, median has to do more with position, and then mean has to do more with value. Think of it that way, because they're both the middle per se, but in different ways. The mode is just the most frequently occurring one. So if you know you have 2, 2, 2, 2, 7, your mode is 2. Outlier would be something like negative 2,000. It's going to be something that's way off track and doesn't fit along with the other pieces of data. So that's what those are. Not too exciting. Oh, like save my. Oh goodness, what? I saved my screen there, so that's nice. Okay, so more stuff on quantitative variables. So we just have here our range, IQR, and our 5-number summary. So our 5-number summary is viewed really easily, as we've been showing on a box plot. Wow, that's just not good. Okay, so our minimum, our smallest value, and then our first quartile is going to be here. Second, our median. Third, where 75% of the data lies below it. Whoa. And then our maximum. So in regards to quartiles, keep in mind that basically, so the first quartile is saying that 20, so this is, oh goodness, it's totally not, can't see that. Okay, so for the first quartile, this is going to be the 25th percentile. So percentile means the percent of the data that lies at or below that piece of data. So for Q1, this means that 25% of the data is right here, is between the median and Q1. For Q2, this means that, so this is the 50th percentile, so that means that 50% of the data lies below this. So if you think about it, this is another 25%, because these are quartiles, quarters, 25. So together, this is going to be 50%. So that's why it's the 50th percentile, because 50% of the data lies below this. What else? Okay, Q3 and 75 percentile, 75th, and you guys probably get the idea. Our range is just our max minus the minimum. So that's everything from here to here. Our range is all this in here. I really just messed up this box, but I'm going to draw a different one for the IQR. And then our IQR is just going to be the range, but your minimum is going to be Q1 and your maximum is going to be Q3. So you're looking for the range in between these two within here. So it's still a range, it just cuts off at Q1 and Q3 instead of the min and the max. That's the only difference. Okay. Let's see. Okay, standard deviation and variance, we talked about this a little bit. So our standard deviation is the spread, so it's how far away the score is from the mean. So like when I was showing you on the normal curve of a z-score, your mean's always 0 and your standard deviation is 1, so that means that your spread is 1 away from the mean. Variance is just the average of all the square distributions, so it's our standard deviation squared. That's all that is. Keep that in mind, because variance is different than standard deviation. If you're given the variance, make sure you square root it to find your standard deviation if you're asked for that too, because they're not the same thing. Okay, empirical rule. I love this. This is like just so, I love the empirical rule. So sweet. So this is talking about, and it goes back to when you have a z-score curve, your mean of 0 and your standard deviation of 1. So it basically describes what % of the data lies below these different, like, where the percentiles are. So let me show you here. So for the first one, I don't know what I did there. So for like 68%, that's talking about that between plus or minus 1 standard deviation, 68% of the data lies within it. So this is 68% of the data that I just scribbled in, okay? Let me erase here. That's cool. No, I didn't want it all like that. Never mind, oh well. All right, so then another way to, another way to do this, then if we're talking about 95%, that's plus or minus 2 standard deviations. So I'm looking at this sentence here. So that's going to be between here and here. This is 95% of the data that I'm shading in, okay? So on and so forth with 99.7, that's going to be with plus or minus 3. That's basically saying that this is almost all of the data in here. It's 99.7% of the data. I didn't do that. My elbow hit. We're okay. All right, so let's clear this. Whew. All right. Okay, so now we're talking about categorical data displays. So kind of switch your mindset. We're talking about labels. There aren't numerical values attached with this per se. These are going to be things that are just different labels and groupings. And we're talking about first with one variable, so one categorical variable. So a frequency table is just talking about, it's literally what it sounds like, the frequency of a variable. So in this case, for this frequency table that I drew here, our one variable is going to be campus, the type of campus, like the name of the campus. That's going to be our one variable. And then all it's showing, this is the frequency part of our, I can't write and talk at the same time. This is the frequency part of our table. So our count. So it's saying the number of students who are at University Park. This is way low. We have like 46,000 now, but it doesn't matter. So that's all that's saying. And then, World Campus. So that's going to be 6245. All it's doing is showing the count. So how often it occurs. Pie chart is good when you want to know percentages, like what percent of the data is a certain category. So, if you were to, put this into a pie chart, it's showing that like almost 50% of the data is represented by University Park students. So that's basically where that comes from. Looks like a pie. That's why it's called a pie chart. It's very visual. This one, frequency table is more, you gotta look into it. Pie chart is very visual. You can see, which slices are smaller and whatnot. So remember, these are categorical data displays. So we're talking about categories and labels. Oops. Okay. Okay, another categorical data display for one variable is a bar graph. So this is once again showing the frequency of a variable. So in this case, we still have our variable as being campus on our x-axis, and all these bars are showing is the frequency of that. So the frequency of the enrollment would, this is saying 40,000, whatever. So here's like your cap. Make sure, so yeah, once again, categorical data, keep that in mind. This is important because you'll, from my experience doing these tutoring and everything, like, you'll get questions like, what would you use for a quantitative data display? Like, would you use a bar graph, a histogram, or a dot plot? Or, no, bar chart, histogram, or pie chart. And, the answer would be histogram because that goes with quantitative data, and not the rest of them are for categorical. So make sure you kind of separate these in your head for that. So, yeah, this is a bar chart. It's also called bar chart, too. You might see that. Or graph, whatever floats your boat. And basically make sure that they're not touching. Remember in histograms, the bars were touching because in values, they can share a number there. So because they're values, so they take numbers on the number line. But when we're talking about categories, they don't share something. So we couldn't, if we put these together, I don't even know what that says. Oh, Commonwealth. If we put these together here, that would be saying that, like, there's a commonality between University Park and Commonwealth, like, together. Like that just doesn't make sense. So that's why we separate them. So make sure if you see something with separations, that's going to be a bar graph and not a histogram. All right. Okay, so now we're still talking about categorical variables, but we're talking about two variables now. So this is similar to a frequency table, but it's a two-way table. So here, instead of having one variable, we have two. So that's going to be, we're going to have gender here. And we're in a normal frequency table, we just have the counts of genders. In this case, we have another variable, which is going to be sports, which is here on our the top of the table. So it's just showing you the different frequencies of where those variables collide. So like females who like basketball will be 16, females who like baseball, 45, males who like football, 40. So yeah, you just like come into where they intersect, the variables, and then that's how you get it. And then your totals are shown here at the bottom. Often you'll see totals shown at the end here for Todd. That you'll see at the end here for like total number of males or whatever. So you'll see that too. So remember, that's categorical data display for two variables. So yeah. Alrighty. So, okay, and a few more for categorical data displays for two variables. We're still talking, these are bar charts. That's why I told you can hear them as bar charts, bar graphs, is the same thing. I usually say bar graph, but I've kind of gotten the habit of saying bar chart, but they're the same thing if you see it written that way. So these are still bar charts, but now we're talking about two variables. You remember if we were talking about one variable, it looked like this. They weren't touching, but it looked like this. But in this case, with two variables, you can see, it's split for a segment or a stacked bar chart. We have one variable here and one variable here. So that's just, and then you obviously want to have a key over here so you know what color means what. So yeah, it's just making sure that, one category is representing the X and then the other one is within the bar. So the category on the X-axis is going to be the sport, and then within the bars, this is going to be our other variable, either won by the visiting team or the home team, and that's what the colors are. Side by side, it's the same idea, two variables for a categorical data display, but instead of being stacked on one another, you still have your key over here for your second variable, and then your other variable is going to be down here. You still have them, the two different variables, but in this case, they're just side by side. So nothing too exciting there. Okay. Okay, probability, everyone's favorite. I know this can be tricky, so like I said, stop me at any time if we're going too fast or too slow. If I'm going too slow, like, let me know. I can definitely speed it up. So probability, the definition, the probability of an event occurring, like how much you think an event's going to occur. We usually write it as decimals, like 0.2, 0.5, whatever, something like that. But obviously, multiply it by 100, that's going to be a percent. So you could say this percent probability, whatever. The probability of event A, that equation there is just saying how to find a probability if your number in group A divided by your total number. So that's the probability that that event will happen. This is just the equation to find it. Probabilities are always going to be between 0 and 1, positive values. You can't have like a negative probability. Probability of 1 means it's 100% certain, and then probability of 0 means it's impossible and it's never going to happen. So that's what that is. Okay, risk and odds. These are commonly mixed up, so make sure you keep these, try to differentiate these, because they both are describing the likelihood of an event happening. But risk is talking about the probability that it's going to occur, but then odds has it in comparison to it not happening. So that's the difference there. So we're both talking about that event happening, but odds has that extra part there versus it not happening. So that's the difference between the two. Yeah, risk, since it's just the probability that an event will occur, that's the same like formula we use for just probabilities. The number with the outcome divided by the total number. So that's risk. Risk is basically the same thing as probability in general. Odds are going to be our likelihood of an event versus not happening. So that's why our denominator in that equation is a little different. So in risk, you see the denominator of the fraction is total number of outcomes, and then odds, it is number without the outcome. So that's kind of how we find it, so that that's how it's different than risk. That's how we add that last part in of not happening. So those are our equations. Okay, so combination of events. So we're talking about categorical variables again. So this would be, the probability that these events happen in this certain type of combination. So we'll go through each of these one by one briefly, because I want to make sure we get to the review questions, because those are usually helpful. So there's just a list of them in table format, but we'll go through each one, like I said. So probability of A and B, that's going to be that blue shaded part in there. It's a probability that both A and B are happening at the same time. And start trying to think of those symbols. So intersection, probability of A and B, that little upside down U. So that's going to mean an intersection. So make sure you don't get that confused with a union. A union is going to be the probability of A or B happening, but make sure that you do include the probability of A and B happening, because if A and B are happening, A or B is technically also happening. They're just both happening. And this is probability of A or B. So the way I look at it, and everyone always makes fun of me every semester, but I'm going to show you anyway. So, because I always had trouble memorizing the symbols, like knowing that, this upside down U meant union. I don't know why, because I mean, it might make sense to people just use union, but to me, I didn't understand if it was, meant like bring it together. But I always think about a little dude, and he's just chilling here, and he's really confused. So he's like boop boop. And Isis remembers this. I did this last semester, and it's just he's like, I don't know, like he's just really like, So and that looks like a U, you know what I'm saying? Like that is a union right there, just like, so that's where it gets from. So that's how I remember it, because he doesn't know if he wants this or this. So that's why he's like, and then it's a union because he makes a U. Okay, that's how I remember it. If that helps. You're probably like, I didn't need to know how to remember it. I already remembered it, but all I know is I had trouble with it. So Some people said it helped them last semester, but so yeah, I think the little IDK guy. People got mad actually when I didn't draw it one time, so I don't know. Maybe I won't get in trouble this time. So that's a union. Let's see. Okay. Another combination of events. We're talking about complements now. So complements is basically when we're talking about all the space except for the event. So let me actually draw like a square around this so it makes more sense. I don't like how it's drawn. So this A superscript C is saying that that's going to be our complement. So that's everything except for A. So everything in this blue circle is A. And all this white space is the complement, A superscript C. So the probability that the event does not occur. So the probability that the event occurs is going to be all this space in A. The probability that it doesn't occur is going to be all this other space in white. And that's what our complement would be. And then this is just another way, like I said, just algebraically, if you were to manipulate this equation, you could get this equation down here, and that's how you could find the probability of A if you're only given the complement, just to switch it around. Okay. Oh. Okay. This is such a struggle. Oh, I clicked something. Okay. Conditional probability. This is talking about, we have two different probabilities here, but they're like relying on one another. So the way you read that PA line B is the probability then of A given B. So the definition of conditional probability, the probability that an event will occur given a second event has already occurred. So something needs to happen before the next event occurs. So that's conditional. Like there's a condition that needs to happen before the next one, like before the other one occurs. So that's just, this equation here is just how you would find a conditional probability if you're given this information. So you would need to have your probability of A intersect B. So probability of A and B divided by the right side of your conditional probability. So the second part, so after the given. So that's going to be your denominator there always. You can, and just to write it out again, if this makes more sense, or just to show you a different way, like if I had probability of B given A, I could write out, probability of B intersect A divided by the probability of A. So you see my denominator is always going to be in regards to this one. That's what I was talking about here, the one to the right. Okay. All right, cool. What else do we got? Okay, independent events are going to be, this is the last slide, then we're going to reviews. Okay, independent events are going to be events that are unrelated. So one event doesn't impact the other one. So that means they're independent of each other. And then if you want to check for independence, but you're only given like probabilities of A and B and conditional probabilities, whatever, and intersection, these three statements are what you can use to check. So you want to see if one side is equal to the other. So if you were to plug in the values you have for like probability of A and probability of B, whatever, if you were to plug them into whatever equation has those values in, you want both sides to be equal. So you want those statements to be true, because if they were, then the left side would be equal to the right side. And then one thing to keep in mind is that if one of them's true, they're all true. That's just how they work out. So you only have to check one of them. So you only have to check, you just want to make sure you choose the one with what you have. So if you're given the value of probability of A given B and the probability of A, you're obviously going to use number 2. And then whatever you get from number 2, you're able to decide whether or not they're independent or not. If that statement was true, you can assume independence because that means the other ones are true too. If that one's false, the other ones are also false, so you can't assume independence. All right, let's do some review questions. Whoop, whoop. Okay, so and if you guys haven't done this before, I just basically read the question and then answer it if you think you got an answer, and then we'll go over together. Okay, so there are 25 children in the class, 15 boys and 10 girls. What proportion of the students are girls? Let's go ahead and see what you guys think, and then we'll go over this one. Yay! Okay, good job. All right, so let's go over this one. So if we're looking for, in this case, we're looking, where's my annotation? Okay. So we're looking for the probability that it's a girl. It's a girl. Baby shower. Okay. So what proportion of students are girls? So that's what we're looking for, the probability that it's a girl. So in that case, remember, probability is going to be the number of the variable that you have divided by the total number. So the number of girls we have is 10, and then divided by our total number is going to be 25. So then this comes out to 0.4. So our answer is C. Doesn't seem like the answer is always C. I'm just kidding. Don't follow that. But so yeah, probability of a girl. Good job. You guys definitely got that one down well. So cool. They'll get harder. Don't worry. Okay. All right. So there are 25 children in a class, 15 boys, 10 girls. If you were to randomly select one child from the class, what are the odds that you would select a boy? So go ahead and try this one out. Whoop, whoop. Okay, cool. So let's go over this one. So remember, odds are going to be the number of our variable that we have divided by the number that it wouldn't happen, like the number that is not that variable. So in this case, so we're looking for the odds that you would select a boy. So remember, odds, if we, actually, can I go back to this slide? Hold up, wait a minute. Go to slide. Yeah. So remember, odds is the likelihood of an event happening versus not happening. So the number with the outcome divided by the number without the outcome. So that being said, what we would do here is our number with the outcome would be how many boys there are, so 15, and then divide it by the number without the outcome. So that would be the 10 girls, because those are going to be the ones that don't have the outcome of being a boy. So we're going to do 15 divided by 10. And then, so what we're going to get is 1.5. So that means that there's a 1.5 chance of it happening to 1. So that's going to be, because the answer what we got was 1.5, and that's going to be to 1. So that means there's 1.5 boys per every 1 girl, which sounds really weird, but in theory, that's just how you make odds. So obviously it doesn't make sense, but that's just what it is. Does that make sense to everyone? All right, so yeah, our answer would be C in that case. Yes, no, baby. Okay, cool. Yay. All right. Yeah, basically. Because what you're finding out is the event of it happening versus not happening. So like I said, you know, and it makes sense in this case because like there's 15 boys, so there's more for 10 girls. So if you think about 1.5 in theory boys per 1 girl. So yeah, basically. Okay, cool. Yay. Good job, guys. Killing it. You guys are definitely being troopers right now. This is a long one, a long presentation. So, all right, let's skedaddle. Number 3. All right, a group of psychology students is studying the vocabulary of 3-year-olds. They take a sample of 35 children and record how many words each child says during a 15-minute session. Which of the following graphical representations should be used to present their data? Let's go ahead and check that one out. Let me know what you think. Yay! Okay, perfect. Good job. You guys are all right. Where did I? Oh, here's my pen. Yeah, so definitely our answer is going to be B, histogram. So basically, we took that sample of 35 children, and then we're studying the vocabulary, and we want to see how many words. So that's going to be quantitative. So we know it can't be bar graph because that's used for categorical data, so that can't be correct. So it's either B or C. Side-by-side box plots, though, is used for if we're talking about 2 variables. We're only talking about 1. We're just talking about our vocabulary, how many words. So answer has to be B. Good job. All right. All right, number 4. Okay, the 5-number summary of the fastest ever driven speed, miles per hour, of 87 Penn State students is 55, 95, 110, 120, and 150. I'd be in the 150 category. What percentage of students reported a fastest ever driven speed of at least 95 miles per hour? Okay, great job. So let's look. So when I do a 5-number summary, I always like to draw it out as a box plot. I like visuals. There's no such thing as being a visual or an auditory learner only. Everyone is a mix of the two, but some people use one more than the other. I study a little bit of psychology, so fun fact. But so if we were to draw this out in a box plot, we're going to have our minimum at 55. Our first quartile is going to be at 95. Second is going to be 110, 120, and then 150. So in this case, if you recall, when we're talking about quartiles, that means that our first quartile is going to be in the 25th percentile. The second is going to be in the 50th. And then this one's going to be in the 75th. So if we're talking about Q1, Q2, Q3. So in any order, so what percent of students reported the fastest ever driven speed of at least 95? So that's going to mean 95 or higher. So if we're looking at it, we're going to start here. At Q1 is going to be our 95. So they're saying at least 95. So that means it could be higher, but like minimum 95. So our minimum is 95 here. So given that, it's going to be everything up to 150. So it's going to be all of this is going to be what we're talking about. So basically, then if you think about this way, so remember, each part of the graph is 25%. So this is going to be 25, this is going to be 25%, 25%, then 25%. So here we have 3 25%. So that's going to end up being 75% of the data. So good job. A+. You guys are doing very well. Seriously. Some people struggle with this stuff. Okay, cool. A distribution has a mean of 95, a median of 87, and a mode of 80. Which of the following describes the shape of this distribution? Yay! Okay, good job. Okay, so this, yeah, you guys are doing great. Awesome. So our answer is going to be B, skew to the right. So remember, when we're looking at values from largest to smallest, it goes from mean, median, mode. So then if we skew images, then that means that we're going to have an exact match on the progression related to that distribution. So that's going to be skewed to the right, because if we look, we have our mean of 95, and then our mode is going to be 80. So, and then our median, yes, and then our median is 87. So if we're thinking about, remember, skewed to the right is going to look like this, more spread out. So, and if you think about it this way, so this shouldn't be 95. So let's say our mean is going to be the center, remember. So this could be 95, and maybe our median's over here at 87, and then our mode is 80. Technically, our mode should be the highest one like the highest point. You guys get the idea, and that's more spread out down here because we don't really have anything going on over here. So skewed to the right. Let me see. I feel like I have a picture. Let me see. Yeah. Okay, cool. So this is another way to remember it for being skewed to the left. Well, for being symmetrical, our mean is equal to our median, which is equal to our mode. So our average is equal to our middle value, which is also equal to our the most commonly occurring value. Skewed to the left, our mean is going to be the smallest, our mode is going to be the largest, and then skewed to the right, mode is the largest, mean is the smallest. So that's another way to think of it. All right, number 6. All right, find the z-score corresponding to a raw score of 109 from a normal distribution with a mean of 100 and a variance of 25. So read this one carefully and try it out. Okay, let's go over this one, see what we got. So, good job, Hannah and Danny. No one, usually people don't get this right, so killing it. Okay, so remember our equation to find a z-score is going to be our original score minus our mean square here, and then divided by our standard deviation from the original score. So keep in mind, variance of 25, that's going to mean that our standard deviation is going to be equal to the square root of 25. Because remember, our variance is equal to our square root, or our square root squared, our standard deviation squared. So standard deviation is actually going to be equal to 5. So if we were to plug all this in, we would do 109 minus 100, so our original score minus this mean, divided by our standard deviation, which would be 5, we found. And then if we solve this, we're going to get 9 over 5, which is equal to 1.8. So great job. Does that make sense to everybody? Woohoo! Yay. Okay, cool. Oh, I just like drew all up on here. All right, let me clear this. Yeah, see, that's what I know. Everyone forget. I told you I gotta make them a little tricky. So yeah, always keep in mind you gotta read like in statistics you gotta read the questions carefully. So yeah, that's what people usually mess up on. But as long as you also understand how to do the actual equation, that's good too. You just want to make sure you pay attention to those little parts. So all right, cool. Oop, oh my gosh, I keep doing this. Okay. All right. At one university, 1 in 7 students who sign up for a course end up dropping or failing the course. Sad. What is the risk of a student at this university dropping or failing a course? Let's go ahead and check that one out. All right, cool. Good job. So our answer is D, definitely. D, definitely. Okay, so remember our risk is going to be our number of the event happening divided by the total number. So our number of the event happening is going to be 1, and our total number is going to be 7, because they're saying 1 out of a total of 7 students. So if we did 1 divided by 7, we're going to get 0.143. So our answer would be D. Make sense to everyone? Or holla if it don't make sense. Okay, perfect, cool. I know, I just give me some feedback, or I'll be talking to myself. Okay, cool. Let's we have 3 more. You guys are hanging in. 11-11. Make a wish. Ah, I cracked myself up. That's all that matters. Okay. All right, number 8. The risk of a certain event is 76%. What are the odds of that event? Let's try this one out. Okay, good job. Good job. Yep, our answer is A. So remember, odds, one of the equations that we can use is going to be our risk divided by 1 minus risk. So if we took this percentage, 76, and divided by 100, we're going to get a decimal, which is how we do probabilities technically. So we're going to get 0.76. So if we were to translate this, we would get 0.76 divided by 1 minus 0.76, and that's going to give us 3.167. And then remember, with odds, we just put that boop to 1. So our answer would be A. Good job. Smells like someone's cooking something in my house and it's burning. I will act like I don't know what's going on. All right. Yay. All right, 2 more, and they're related to each other. Okay, at one university, 88% of students speak English, 60% of students speak French, and 50% of students speak both English and French. Are speaking English and speaking French independent events or not? Okay, cool. So let's go over this. So remember, so one of the ways that we can check for independence is doing like our probability of A times our probability of B, and then seeing if it's equal to our probability of A and B. This was one of those three equations that you could use to check for independence. And you're always just going to use the one that you have information for. So in this case, we have enough information for this one. So if we did like, let's say we did, we'll say that A is going to be this English for English, and then this 60% is going to be B. So if we were to write that out, it would be 0.88 times 0.6. So that's probability of A times probability of B equals the probability of A and B, which would be 50%, because 50% speak both English and French. So theoretically, what we want to do is check if this is correct. But if you multiply 0.88 times 0.6, you're actually going to end up getting 0.528. And that is not equal to 0.5. Therefore, they are not independent. Does that make sense? Yes, because if one of them's not true, then that means that they're all not true. Okay. Yeah, good question. Yeah, it has to be like exact. It has to be exactly like 0.5 equals 0.5. That's the only way. There's no rounding or anything. So, but good. That was a good good idea, definitely. You're welcome. All right. One more question. You guys are like, thank God. All right. All right. So at one university, 88% speak English, 60% speak French, 50% speak both. It's the same scenario as the last one. What's the probability that a randomly selected student speaks either English or French? So try this one. All right, cool. Let's go over this. So remember this one's asking about probability of A or B. So if we're doing English and French, I could do it like this, like E or French. So English or French. So remember what we do for this one. We find probability of English and French and then subtract both. So we're going to have 0.88 plus, so that's our probability of English, plus our probability of French, and then minus the probability of both. So we want to make sure we do this first, though, put that in parentheses, and then we'll get 0.98. And think about that, because this makes sense, because it says that 88% speak English, 60% speak French, so, and then 50% speak both, so it's saying what's probability that they speak either English or French? Like, that's almost all of them, you know. So after you get your answers, this is something you should definitely do in statistics. After you get your answers, think back and be like, does this even make sense? So if you got a different answer, first of all, it has to be between 0 and 1. But if you got a different answer, you want to check, like, does it make sense that it's this answer or not? So, but yeah. All right, cool. Good job, guys. You guys did a great job. A very smart group we got. Okay, so yeah, you can obviously check out this recording and all the rest of them on my YouTube channel, which is so weird to have. And our next group review is going to be on Sunday at 10 again. It'll be the same structure. Bye. It'll be the same structure, the same review. Unless if you have other questions, you can bring them then. So yeah, if you haven't given me, of course. All right, sounds good. I'll be here on Sunday too. Woohoo! So yeah, if you haven't already given me your email, go ahead and put that in the chat box. If you have any other questions, let me know. Except you guys are probably done with stat for a while. So, but yeah, hope you guys have a great night. And let me know if you need anything else. I'll see some of you Sunday or whenever. Okay, cool. I hope it was helpful. Thank you. I'm glad it was. Yeah, if there's anything else you guys ever need, let me know, and we will make sure to add that in there, takeaway or whatever. So, thank you, Brandon, and you're welcome.